A telescope more than 1 million miles from Earth is quietly changing everything we thought we knew about the universe. The James Webb Space Telescope has captured details that were once hidden in the depths of time. This year alone, its discoveries have already changed the way we think about the birth of stars and the formation of galaxies several times over. The uniqueness of JWST lies not only in the beauty of the images but also in the accuracy of the data. Galaxies that once appeared to us as dim spots now reveal their structure, star formation rates, and even the violent processes that govern their evolution. The telescope's unprecedented resolution allows us to peer into the regions where stars are born, giving us a glimpse of the complex interactions that shape the modern universe. In this video, we've compiled the most remarkable discoveries made by JWST this year, each one putting our previous theories to the test, each one bringing us closer to answering fundamental questions about the universe and our place in it. Galaxies and their endless interactions often create strikingly beautiful yet scientifically profound visual images. One such example, observed by the James Webb Space Telescope this September, is the collision of two galaxies known as ARP-107. This event bears an unusual resemblance to a smiling face. The collision, occurring about 465 million light-years away in the constellation Leo Minor, involves a large spiral gateway and a smaller elliptical galaxy. The JWST's near-infrared camera and mid-infrared instrument revealed intricate details that stunned astronomers. Most noticeable in this cosmic smile is the nearly transparent bridge of stars that's been pulled from both galaxies and stretched between them like a thin thread. Areas of active star formation, new stars born from turbulent gases displaced by the merger, glow in orange and red hues. This image tells us about the processes that occur during collisions of this magnitude. Events like this can have two seemingly contradictory effects on galaxies. On the one hand, disruption compresses gas clouds, which accelerate star formation, creating clusters of newborn stars in regions where galaxies collide. On the other hand, collisions can disperse and accelerate gas, depriving parts of galaxies of material which can lead to the starvation of stellar birth in other regions. What's even more interesting is that the large spiral galaxy in this system is classified as a Seyfert galaxy, one of the largest families of active galaxies. Such galaxies have high-energy nuclei dominated by supermassive black holes. In the case of ARP-107, the central region of the spiral galaxy emits energy at a level far beyond that which can be explained by ordinary stars. However, unlike the most active galaxies, Seyfert galaxies such as ARP-107 are less bright, making them easier to study in the infrared spectrum, the main band used by JWST. The collision also sheds light on how such structures evolve under gravitational influence. Despite the event, the galaxy retained much of its overall structure, except for its distinctive spiral arms, which were almost completely obliterated. This observation demonstrates how even off-center collisions can cause significant changes without destroying the entire system, and contrasts greatly with the more direct, head-on mergers that typically produce chaotic, irregularly shaped galaxies. ARP-107 today continues its slow gravitational absorption, which will continue for hundreds of millions of years, eventually forming one large, irregularly shaped galaxy. Such things are not uncommon in the universe, but the details that JWST provides allows us to observe and analyze these processes like never before. A little earlier, JWST also shed light on details about another interesting galaxy that has given us important clues about the cycles of birth and destruction that shape the cosmos. Located about 15 million light-years away, M83, also known as NGC 5236, stands out among spiral galaxies not only for its characteristic barred structure, but also for the active stellar processes taking place within it. The center of M83 is a hotbed of star formation, especially visible in the intense blue regions captured in JWST images. Here we see a huge cluster of stars closely clustered together. Even more exciting are its spiral arms extending from the core regions known as stellar nurseries. These regions, where new stars are actively being born, are highlighted in bright yellow and orange colors in MIRI images. They're rich in gas and dust, particularly polycyclic aromatic hydrocarbons, complex carbon-based molecules that often accompany star formation. JWST's ability to detect these compounds is crucial for studying the chemistry of star-forming regions, allowing us to understand the building blocks of the stellar life cycle. By observing M83 at wavelengths between 5,000 and 28,000 nanometers, Webb can penetrate through the dust that normally hides these stellar nurseries from optical telescopes. These detailed images provide a fundamental tool for understanding the process known as stellar feedback, how young, newly born stars interact with their environment. When forming, stars release energy and eject material in the form of stellar wind and radiation. This feedback can either compress nearby gas, triggering further star formation, or disperse the gas, stopping the birth of new stars in surrounding regions. By carefully studying galaxies like M83, researchers working on programs such as Feedback and Emerging Extragalactic Star Clusters, or FEAST, seek to unravel how such feedback mechanisms operate in different galactic environments. The results obtained on M83, as well as on other galaxies in the FEAST program, will help refine the models that astronomers use to simulate star formation throughout the universe. Another JWST observation of the N79 nebula, this time in January, has presented us with one of the most active star-forming regions in our galactic neighborhood. Located about 161,000 light-years away in the Large Magellanic Cloud, N79 is a prime example of a star factory, where new stars are forming at a highly accelerated rate. Unlike its better-known neighbor, the Tarantula Nebula, N79 has remained relatively unexplored until now. The striking starburst pattern emanating from nebula's core is immediately apparent in the JWST image. This effect is not an intrinstic feature of the nebula, but rather a consequence of the way JWST's segmented primary mirror collects light from particularly bright objects. These diffraction peaks emphasize the intense light of a young forming star, barely visible in the visible wavelength range, but revealing through the power of infrared observation. The orange and red regions surrounding this core are huge clouds of molecular gas, the raw material from which new stars form. In these regions, massive clumps of cold hydrogen gradually condense under the action of gravity, triggering the star formation process. Protostars, still in their native gas envelope, are particularly important for understanding stellar evolution. They represent the initial stage of a star's life when nuclear fusion has not yet begun in their cores. a mass is gained from the surrounding gas envelopes. They'll eventually reach a point where the internal pressure and temperature become sufficient for hydrogen to fuse into helium, officially marking the birth of a full-fledged star. Another exciting aspect of the discovery of the N79 nebula is its potential to shed light on the early universe. By studying local processes, astronomers can gain insight into the conditions that prevailed during the most intense period of star formation in the cosmos. Also this June, Webb gave us another interesting example of star formation by observing the spectacular Serpens Nebula. In this region, located about 1,300 light-years from Earth, a remarkable phenomenon has been observed. Protostellar outflows, jets of gas erupting from young stars. Although such outflows have been observed before, the accuracy and clarity left much to be desired. These jets represent one of the earliest stages of a star's development. When the gas collapses under gravity to form a protostar, some of the material is trapped in jets that fly out of the star's poles at incredible speeds. However, the unique arrangement of these jets in the Serpens Nebula provides new insights into a process that until now could only be hypothesized. The jets flowing in the same direction provide strong support for the long-standing theory that stars forming in the same region orbit in the same direction. What makes this discovery even more significant is the permanence of this alignment, which NASA scientists have likened to sleet falling during a storm. This metaphor emphasizes the striking orderliness in the chaotic environment of star birth. The implication's obvious. These aligned flows serve as a kind of historical record of the rotational dynamics in the gas and dust clouds. As stars form, they inherit the angular momentum of the collapsing cloud, which leads to synchronous motion. One of the most striking aspects of this photo is the appearance of an hourglass-shaped shadow cast by one of the young stars. This shadow is a direct result of the jets giving the surrounding gas such a striking shape. JWST's nebula observations are not just limited to star formation. They also provide crucial information about the evolution of the disk and material surrounding these young stars, key ingredients for planet formation. By capturing these jets so early in the development of stars, astronomers can begin to piece together the complex processes that lead to the creation of planetary systems. But Webb's June discoveries don't end there. WASP 39b, a gas giant located 700 light-years from Earth, represents one of the most intriguing planetary environments ever observed. Thanks to the unprecedented sensitivity of the Space Telescope, we now have a clearer picture of the extreme climate of this exoplanet, a world divided between eternal day and endless night. This exoplanet is in tidal lock, meaning that one side of it is always facing the star and basking in the sun's rays, while the other is in perpetual darkness. This sharp separation creates a unique atmospheric environment that precisely rejects the possibility of life and takes our understanding of planetary climate dynamics to a new level. The JWST near-infrared spectrograph allowed astronomers to measure the temperature differences in these regions with an astonishing level of detail. At first glance, it may seem like a world of absolutes. Scorching heat on one side and icy cold on the other. But the real allure lies in the so-called gray zone between these extremes, where the temperature transitions from the day side to the night side. NIRS data shows that the temperature difference between the dawn and twilight regions is an impressive 300 degrees Fahrenheit. On the dawn side, the temperature stays around 1,150 degrees Fahrenheit and rises to about 1,450 degrees Fahrenheit in the evening. JWST also discovered impressive weather patterns on the exoplanet. Wind sweeps across the surface at astonishing speeds of thousands of miles per hour, transferring heat from the day side to the night side. And this atmospheric circulation is critical to maintaining the balance of temperature on the planet. Interestingly, the dawn side, where night turns to day, tends to be more cloudy. Thick layers of gas form in this colder region. In contrast, the evening side, where day turns to night, appears much clearer, with fewer clouds, perhaps a result of the warmer temperatures displacing condensed gases. These discoveries challenge previous models of exoplanet atmospheres, especially on worlds in tidal capture. Understanding how atmospheric circulation, temperature variations, and cloud formation act on WASP 39b provides insight into how planets with extreme climates can evolve. More importantly, it opens new avenues in the search for potentially habitable planets, as scientists can apply these observations to smaller, rocky exoplanets that may have similar gaps between day and night. By precisely measuring the composition of its atmosphere, JWST has detected trace amounts of molecules such as water vapor, carbon dioxide, and sulfur dioxide, giving us insight into the chemical processes that take place on similar planets. This detailed analysis of the atmosphere is of great importance to the search for life beyond Earth, as it allows astronomers to improve their methods for detecting biosignatures. A month later, in July, Webb pleased with another discovery. This study, published in the monthly notices of the Royal Astronomical Society, concerned brown dwarfs, but this time was more extensive. Brown dwarfs, often referred to as failed stars, occupy an interesting intermediate position between planets and stars. Although they lack the mass to ignite nuclear fusion in their core, their atmospheres are far from quiet. The James Webb Space Telescope recently allowed us to study in detail the chaotic weather systems of two nearby brown dwarfs, WISE 1049a and WISE 1049b. These observations have given us a rare glimpse into the atmospheric processes of these enigmatic objects and hint at what we can expect from giant exoplanets with similar conditions. The weather here is far from ordinary. Infrared instruments have shown that both objects are engulfed by colossal, turbulent clouds composed of silicate grains, essentially hot sand swirling in the atmosphere. These clouds, fanned by winds moving at tremendous speeds, create a dynamic environment with temperatures ranging from 1,610 degrees Fahrenheit to 1,880 degrees Fahrenheit. Both bodies rotate at an astonishing rate. WISE 1049a completes a full revolution every 7 hours, and its brother B even faster, in 5 hours. This rapid rotation contributes to the extreme variability observed in their atmospheres. However, the observations do allow us to see how the atmospheres change over time. JWST has taken pictures of the light curves of these brown dwarfs, which show significant variations, indicating stormy weather conditions and shifting cloud cover at different. The light curves obtained with JWST show how clouds evolve at different altitudes, sometimes exposing deeper layers of the atmosphere through gaps in the cloud cover. These variations are associated with different chemical compositions at different depths of the atmosphere. By examining specific wavelengths of light, JWST has found evidence of carbon monoxide, methane, and even silicate grains absorbing into the atmosphere. Each of these chemical markers tells a story about temperature and pressure at different depths, offering a vertical profile of brown dwarfs' atmospheres. Observations indicate that each brown dwarf has 3 distinct atmospheric layers. The deepest layer emits light with wavelengths of less than 8.5 microns, while the intermediate layer absorbs light in the range of 2.3 to 4.2 microns. The uppermost layer, where silicate clouds are most visible, emits signals between 4.2 and 8.5 microns. These results have allowed scientists to study the dynamic nature of brown dwarf atmospheres in unprecedented detail, which was not possible with previous observations. And more importantly, refine models that will help us understand the atmospheres of distant exoplanets, especially those that are too far away to study in such detail. Among the many spectacular images taken by the James Webb Space Telescope, one stands out not only for its beauty, but also for the questions it raises, literally. Against the stunning observation of star formation, a disk resembling a question mark stands out in bright red. This unexpected shape, also captured this July, is most likely the result of an interaction between the galaxies of the Herbig-Haro 4647 complex. Although visually striking, the object's true nature remains a mystery. Initial analysis by scientists at the Space Telescope Science Institute suggests that it's likely a distant galaxy or possibly 2 galaxies in the process of merging. The red hue of the object in the near-infrared JWST image indicates that it is incredibly far away, perhaps billions of light years from Earth. This distance not only makes it difficult to study the object, but also places it in a period of the universe's history when galaxy interactions were more common, galaxies were still forming and evolving. Galaxy mergers are a powerful cosmic phenomenon that can change the shape of galaxies, creating long, curved tidal tails and arcs. And these features are formed as the mutual gravitational forces of galaxies stretch and distort their outer regions. The shape of the question mark may be a similar result of tidal interactions. The curved upper part represents a galaxy being pushed apart by gravitational force, while the lower point is possibly a smaller companion galaxy. The formation of galaxies, especially in the early universe, remains one of the deepest mysteries of cosmology. Webb's observations have provided new insights into this process, especially in the case of 3 galaxies discovered earlier this year that formed between 400 and 6 million years after the Big Bang. In the early days of the universe, neutral hydrogen gas filled the cosmos, forming a thick opaque fog. When galaxies like those observed by JWST began to form, their light helped lift this fog, eventually revealing the modern universe to us. These galaxies have not yet fully formed, but they're still feeding off nearby clouds of gas, mostly hydrogen and helium, the basic building blocks for star formation. Infrared capabilities have allowed astronomers to observe how this gas is absorbed by galaxies, providing a direct view of the galaxy formation process. One of the most remarkable aspects of these galaxies is their association with powerful satellite jets. During the formation of galaxies, their central regions often host supermassive black holes that exert an intense gravitational influence on the surrounding space. When matter falls toward the black hole, some of it's accelerated and ejected as powerful jets hurtling through space at nearly the speed of light. These jets, often observed in young galaxies, play an important role in regulating star formation, as they can either stimulate or suppress the formation of new stars depending on how they interact with the surrounding gas. 3 recently discovered galaxies are particularly interesting because they can provide insight into this process at a very early stage in the history of the universe. In these galaxies, jets from nascent supermassive black holes should still be interacting with the surrounding primordial gas, but not yet have had time to fully trigger the star formation process. Probably these galaxies are in a transitional phase, on the threshold of the birth of the first generation of stars. This process should take millions of years. These observations are particularly interesting because they are the first direct images of galaxy formation ever obtained. Before JWST, astronomers could only speculate about how galaxies form by studying more evolved systems. Now, for the first time, we can observe the earliest birth stages of their growth and evolution and how the interactions of gas, stars, and black holes shape the universe. As the James Webb Space Telescope continues its mission, each new discovery changes our understanding of the universe. From the birth of stars to the mysteries of distant exoplanets, JWST not only answers age-old questions but also opens up entirely new ones, pushing the boundaries of our knowledge. Continued research and exploration are crucial. We look to the future and the coming discoveries that will inspire new generations to keep looking, asking questions, and reaching for the stars. What if the greatest mystery in physics, the invisible force shaping galaxies, never existed at all? For decades, scientists have pieced together a picture of the universe that depends on hidden mass, 5 times greater than everything we can observe. However, a single set of observations from a modern telescope has begun to unravel this carefully constructed concept. Thanks to its unprecedented ability to peer into the early universe, the James Webb Space Telescope has identified galaxies so massive and luminous that they defy all predictions of our most reliable models. These discoveries not only challenge our understanding of dark matter, but also make us question whether gravity itself might behave differently in the distant corners of the cosmos. In early 2023, a research team led by Ivo Labi made a discovery that shook the astrophysics community. Using the advanced infrared capabilities of JWST, they identified 6 galaxies so distant that their light began its journey over 13 billion years ago. These galaxies were not only remarkable for their age, but also for their unexpected mass and brightness, far exceeding what would be anticipated for objects formed so soon after the Big Bang. The brightness of a galaxy often directly correlates with its mass. Brighter galaxies generally contain more stars, and therefore more mass. To estimate this mass, astrophysicists rely on models that assume a certain efficiency of star formation, such as how much gas in a galaxy turns into stars, and a property called the initial mass function. The IMF describes the distribution of stellar masses in a galaxy from smaller, cooler stars to massive, short-lived ones. Herein lies the first problem. These models are based on assumptions derived from studying galaxies in the modern universe, like our Milky Way. Applying the same assumptions to galaxies formed billions of years earlier introduces uncertainties. For instance, if more massive stars formed in the early universe than expected, the resulting light output would increase without necessarily indicating greater total mass. Even accounting for these uncertainties, Labi's galaxies still appeared too massive. According to existing models, The universe hadn't been around long enough at that point to form galaxies of this scale. This discrepancy raises a crucial question. Are our models of early galaxy formation flawed, or do these galaxies possess fundamentally different characteristics? Some researchers point to another potential source of confusion: supermassive black holes. These cosmic giants reside at the centers of many galaxies and can emit extraordinary amounts of light as they consume nearby matter. If the light observed from Labe's galaxies included significant contributions from black holes, the estimated masses might have been artificially inflated. This multifaceted problem goes beyond reconciling observations with current models. It highlights the challenges of interpreting data from the early universe, where assumptions about star formation, stellar populations, and the role of black holes intertwine in unexpected ways. When discussing existing models, we're primarily talking about the Lambda-CDM model, which is the cornerstone of modern cosmology. It provides a comprehensive framework for understanding the evolution of the universe, from the Big Bang to the complex structures we observe today. Its name reflects two primary components: lambda, representing dark energy that drives the accelerated expansion of the universe, and cold, dark matter, an invisible form of matter that neither emits, absorbs, nor reflects light. Cold dark matter plays a critical role in shaping the universe. According to Lambda-CDM, vast clouds of dark matter acted as gravitational anchors in the early universe, drawing ordinary matter together to form stars and galaxies. Without dark matter, the formation of these structures would have taken much longer, resulting in a much darker and emptier universe. The model has proven remarkably successful. It accurately predicts the large-scale structure of the cosmos, from galaxy clusters to the cosmic microwave background radiation. It also explains phenomena such as flat galactic rotation curves, where stars at the edges of galaxies move faster than expected, a problem traditional gravity could not resolve. However, observations from the JWST have revealed cracks in this seemingly unshakable model. By peering into the depths of the early universe, the telescope discovered galaxies that appeared too massive for their age. According to Lambda-CDM, such galaxies should not exist in the quantities or sizes observed. Finding twice as many massive galaxies as the model predicts forces us to confront an unsettling possibility. The model might not fully capture the dynamics of galaxy formation in the infancy of the universe. One of the central tenets of Lambda-CDM is the principle of hierarchical structure formation. This principle suggests that small structures, such as dwarf galaxies, form first. Over time, they merge to grow into the massive galaxies we see today. Yet the galaxies discovered by JWST challenge this idea. Instead of gradual growth, these galaxies appear to have formed quite rapidly, contradicting the slow, step-by-step process predicted by Lambda-CDM. This discrepancy raises fundamental questions about the assumptions at the core of Lambda-CDM. Could the inconsistencies be explained by variations in star formation rates or environmental factors in the early universe? Or do they point to a deeper problem, requiring a reevaluation of the role of dark matter or even the nature of gravity itself? Consider the earlier mentioned puzzle of flat galactic rotation curves. Why stars at the outskirts of galaxies move at the same speed as those closer to the center. This anomaly gave rise to the idea of modified Newtonian dynamics. Proposed in 1983 by Mordechai Milgrom, MOND offers an alternative to the concept of dark matter. Instead of invoking an invisible substance to explain these rotations, MOND suggests modifying the laws of gravity at extremely low accelerations. MOND alters Newton's inverse square law of gravity, proposing that at very low accelerations, such as those experienced by stars at the edges of galaxies, gravity weakens more slowly than traditional models predict. This adjustment successfully explains flat rotation curves without requiring dark matter halos. The launch of JWST has opened new avenues for testing MOND's predictions. In a recent study, Stacy McGaugh and her co-authors argued that supermassive galaxies detected by the telescope align better with MOND than with Lambda-CDM. MOND naturally predicts the existence of massive galaxies in the early universe, as the theory does not rely on hierarchical formation. Instead, galaxies can form quickly and achieve significant mass without the extended timescales proposed by dark matter models. MOND's predictions are particularly relevant at high redshifts, where JWST observed massive galaxies existing at a time when, according to Lambda-CDM, such structures should not yet have formed. McGaugh's team emphasizes that the rapid assembly of massive galaxies could arise naturally within MOND's framework, which does not require the scaffolding provided by dark matter. Despite its success in explaining certain phenomena, MOND faces significant challenges. One of the most pressing issues is its inability to provide an all-encompassing cosmological model. While Lambda-CDM integrates dark energy and dark matter into a cohesive structure, MOND struggles to account for the large-scale structure of the universe or phenomena like the cosmic microwave background. Additionally, contemporary interpretations of MOND often rely on theoretical simplifications. For example, McGaugh's team uses a monolithic galaxy formation model, assuming that galaxies form large and early without hierarchical merging. While these methods simplify calculations, they may not represent physically realistic processes, leaving MOND open to criticism for its lack of predictive power in dynamic scenarios. And finally, this theory has yet to explain phenomena such as galaxy cluster collisions, where the gravitational influence of dark matter has been observed indirectly. This lack of universality continues to tilt the balance of evidence in favor of Lambda-CDM, even as MOND gains traction in specific areas. As JWST gathers more data, MOND's relevance will continue to be tested. If further evidence supports the rapid formation of massive galaxies at high redshifts, it could compel cosmologists to reconsider their understanding of dark matter, or at least acknowledge MOND's potential as a complementary framework. At this stage, one thing is clear. As our scale of the observable universe expands, so do the challenges in interpreting what we see. One key area of uncertainty is related to the estimated masses of early galaxies. The discovery of galaxies that are too massive for their age raises potential errors. For example, if early galaxies contained a higher proportion of massive stars, their brightness and consequently their estimated mass would be overestimated. Additionally, the presence of supermassive black holes at the centers of these galaxies could further skew measurements. As black holes consume nearby material, they emit extraordinary amounts of light, which might be mistaken for starlight. Another layer of uncertainty lies in the way of measuring distances between galaxies and therefore their ages. Spectroscopic redshift measurements, which analyze the light spectrum from galaxies, are much more accurate than redshifts based on images. However, spectroscopic data is limited due to the time and resources required for detailed measurements. Most distant galaxies discovered by JWST have redshifts derived from images, which are based on modeling and prone to inaccuracies. For instance, in this graph, the diagonal green lines indicate where photometric and spectroscopic redshifts align. Ideally, all data points should lie along this line. However, you can see scattering around the line, especially at higher redshifts, indicating deviations in photometric estimates from precise spectroscopic measurements. Why does this matter? because these inaccuracies can cause galaxies to be placed further back in time than they actually are, exaggerating their apparent size and mass. As spectroscopic data accumulates, some of these anomalies may be resolved, reshaping our understanding of the early universe. While JWST provides revolutionary discoveries, additional data from other observations also challenge our current models. One such method is weak gravitational lensing, where subtle bending of light from background objects reveals the gravitational influence of foreground galaxies. Recent studies have used this method to measure the rotation curves of galaxies at distances far beyond what traditional methods can achieve. These results reveal something unexpected. Rotation curves remain flat even at distances up to 1 million light-years from the galactic center. According to dark matter models, the influence of dark matter halos should diminish at such extreme distances, yet this does not align with the data. The finding lends weight to MOND predictions. MOND suggests that at low accelerations, gravity behaves differently, maintaining flat rotation curves without requiring dark matter halos. In contrast, dark matter models fail to explain why their predicted halos do not taper off as observed. However, as mentioned earlier, while MOND explains these rotation curves, it fails to account for the average cosmic amount of dark matter in galaxies and intergalactic space. Dark matter models predict the correct ratio of visible to invisible matter on a cosmic scale, which MOND has yet to replicate. Both the Lambda-CDM model and the alternative physics have their strengths, but recent discoveries challenge the boundaries of both. For decades, dark matter has been the cornerstone of cosmological models. Its influence explains flat galaxy rotation curves, the gravitational binding of galaxy clusters, and the large-scale structure of the universe. Models incorporating dark matter successfully reproduce much of what we observe, from galaxy formation to the cosmic web structure. However, dark matter is not without its challenges. MOND and other alternative theories highlight gaps, particularly in cases like the bullet cluster, where the distribution of dark matter does not fully align with observations. Additionally, data from Gaia has raised questions about the behavior of dark matter in local stellar systems. Despite its successes, dark matter has a significant shortcoming. It has never been directly detected. Decades of experiments searching for dark matter particles have yielded no definitive results. Furthermore, findings from JWST, particularly the abundance of massive early galaxies, challenge the predictions of Lambda-CDM models based on dark matter. One possibility is that Lambda-CDM remains valid but requires parameter adjustments. Modifying factors such as star formation efficiency or the initial mass function in early galaxies could reconcile JWST observations with existing models. These refinements would allow dark matter to retain its central role in cosmology while accommodating new data. For MOND, on the other hand, JWST presents an opportunity to test its predictions. One of the key tests concerns the timing of reionization. MOND predicts an earlier onset of reionization, and upcoming JWST observations could potentially confirm this. Developing a complete cosmological model incorporating MOND is another key step. If successful, it could emerge as a viable alternative to dark matter. The debate continues. Is the universe shaped by invisible matter, or do the laws of gravity require rewriting? Our discoveries so far provide no definitive answer. Whether it involves refining our understanding of dark matter or rethinking fundamental gravitational laws, recent data and research reveal that the universe is far more complex than we imagined, urging us to keep exploring. Among the mysteries of the cosmos, the true titans of the universe are the stars. Imagine a star of unfathomable size and power, so huge that it eclipses our Sun, making it a speck in comparison. Today we turn our eyes upward, not just to admire the beauty of stars, but to go in search of colossal, extraordinary, the largest stars known to science. Our Sun, the heart of the solar system, is just a speck of light against the backdrop of these giants. Stars so huge that they can encompass not only Earth or the inner planets, but extend beyond the orbit of Mars and in some cases, even further. But what makes a star big? Is it mass, volume, or perhaps their effect on the surrounding cosmos? Our quest doesn't end with size alone. We'll look into the hearts of these giants, exploring the nuclear furnaces that fuel their glow and forces that may one day bring about their spectacular demise. Are you ready to explore the limits of the known universe and look into the heart of these space giants? Let us embark on a space journey that begins right here on Earth. Our planet, though conveniently just a speck in the grand scale of the universe, will be the starting point on the timeline. Now let's move on to Jupiter, the colossus of our solar system. It's not just another planet, it's a completely different beast. Jupiter is 11 times larger than Earth and 300 times more massive. Our first step toward understanding the vastness of the cosmos. Jupiter serves as a cosmic bridge from rocky worlds like ours to the gaseous worlds. It's composed mostly of hydrogen and helium, the same components that make up stars. It's not just a larger version of Earth, it's a fundamental shift in composition and characteristics, a formation that is beginning to take on the characteristics of the stars that light up our night sky. In cosmic science, mass and volume are key to understanding the difference between such giants and stars. Mass tells us about the gravitational power of an object and its ability to fuse elements in its core, determining its life cycle. Volume, on the other hand, gives us an idea of size and how much space this body occupies in outer space. These differences are fundamental to understanding the true nature of stars. It just so happens that the smallest mass of a gas cloud that can collapse to form some sort of star is about 1 Jupiter mass. It is at this mass threshold that we encounter a fascinating class of objects known as sub-brown dwarfs. These mysterious entities, often called rogue planets, are on the boundary between the largest planets and the smallest stars. They have the same composition of hydrogen and helium as Jupiter, but on a larger scale, at times leaning toward the deuterium burning mass that is the threshold for brown dwarf classification. However, sub-brown dwarfs lack the mass required for sustained hydrogen fusion, the hallmark of a true star, putting them at a cosmic impasse. With masses below the threshold required for thermonuclear fusion, they occupy a unique niche in the cosmic continuum for understanding the formation and evolution of celestial bodies. As we go deeper into space, we encounter the already mentioned brown dwarfs. These failed stars are interesting because they cannot sustain hydrogen fusion in their cores, a process that defines true stars. With masses ranging from 13 to 80 times that of Jupiter, they're much heavier than any planet, but they still lack the mass to ignite the nuclear fire that powers stars like our Sun. Because of this, they're in a cosmic limbo, glowing dimly from the heat of their formation, but never achieving the full nuclear fission that characterizes full stellar life. Moving beyond the realm of substellar objects, we enter the realm of red dwarfs. the most common and long-lived stars in the universe. These tiny stars mark the threshold beyond which stable hydrogen fusion begins, making them the main sequence stars that populate our galaxy in vast numbers. Red dwarfs are the founders of the cosmos, with lifespans of trillions of years, far surpassing the longevity of stars such as our Sun. Their longevity and abundance make them prime candidates for the search for extraterrestrial life, as their stable and long-lived nature gives enough time for planets in their habitable zone to potentially develop complex life forms. It is also interesting that these are the only main sequence stars that do not grow in volume when they die, simply go out towards the end. Incidentally, the closest red dwarf to us, Barnard's star, is 5.96 light-years away and is the fourth closest star to the Sun after the three components of the Alpha Centauri system. Its stellar mass is about 16% of the Sun's mass, and its diameter only about 1/5 of the Sun. Despite its proximity, the star is invisible to the naked eye. As we move away from the dim glow of red dwarfs, we reach the familiar warmth of our own Sun. The Sun, a main sequence star, is the baseline for understanding stellar magnitude. Its mass, brightness, and lifespan are the yardsticks by which we measure the true giants of the cosmos. With a temperature twice that of Barnard's star, the Sun shines several hundred times brighter than it. Moving on, we encounter Sirius, the brightest star in our night sky. Twice as massive as our Sun, its brilliance depends not only on proximity but also on its own luminosity. It shines 25 times brighter than the Sun. At this stage, relatively small changes in mass correspond to an unimaginable increase in the brightness of main sequence stars. However, by burning its material so vigorously, the star shortens its lifetime by a factor of 4. The journey doesn't end there. Beta Centauri, a binary system, showcases stars whose masses are 10 times that of the Sun and whose surfaces blaze at unimaginable temperatures, 2.5 times that of Sirius. Such incandescence causes them to shine 20,000 times brighter than our Sun. However, possessing a rather impressive mass, scientists have diagnosed its lifespan at only 20 million years. Our journey through space brings us to the threshold of giants and hypergiants, stars that challenge the size limits of the stellar world. Hypergiants, larger than supergiants and giants, are rare stars that shine extremely brightly. By studying their enormous size, radiated power, and intriguing aspects of their measurements, we're discovering new information about the life cycles of the most massive stars in the cosmos. In a world of giants, UY Scuti, Stevenson 218, and WOH G64 are monumental figures, each embodying extreme aspects of stellar evolution. UY Scuti, a red hypergiant in the constellation Scutum, is known for its huge radius, making it one of the largest observable stars. Back in 1860, German astronomers from the Bonn Observatory first cataloged UY Scuti. A few years ago, this star gained lots of popularity as the largest star known to us. However, recent recalculation of distances has pushed it back down the list. The star is located near the center of the Milky Way, about 5,900 light-years from Earth. UY Scuti is nearly 800 times the size of our Sun. A star of this type loses most of its mass due to fast-moving stellar winds that take some of its materials with them. However, for all that, while remaining quite impressive, our candidate now does not even make it into the top 80 largest stars known to us. Stephenson 218, another red supergiant thought to be the largest just a couple of years ago. The star's radius is estimated by some sources to be 2,150 solar radii. To make you realize the size, if you put the star in our solar system, Saturn's orbit would girdle its radius. And if you wanted to orbit it at the speed of light, one lap would take you an astonishing 9 hours. For example, the same trip around the Sun would only take 14.5 seconds. However, its luminosity is well above the Humphreys-Davidson limit, which we'll discuss later, and perhaps for this reason, it's not a member of the Stephenson 2 cluster, which makes its location, as in the case of UY Scuti, closer, and consequently its size much smaller. So who actually takes first place, you ask? As of today, according to the list of the largest known stars, the leader is WOH G64. It has a radius of 1,540 solar radii. This means that if the star were at the center of our system, it would swallow the orbits of Mercury, Venus, Earth, Mars, and even Jupiter. This radius even fits within the stellar evolution limit, which we'll discuss next. Across the vastness of the universe, astronomers use state-of-the-art techniques to measure giant stars. One such method involves the use of spectroscopy, an instrument that analyzes the light emitted by stars. By decomposing starlight into its constituent colors, spectroscopy can determine the chemical composition, temperature, density, and relative motion of these celestial giants. This technique has played a crucial role in the study of WOH G64, revealing its enormous size and the intricate details of its surrounding dust envelope. Another innovative approach is interferometry, which combines the capabilities of multiple telescopes to model a larger aperture. This method greatly improves resolution, allowing astronomers to distinguish surface features and angular sizes of distant stars. The use of interferometry has led to breakthroughs in understanding stars such as UY Scuti and Stephenson 218, allowing us to understand their physical size and surrounding circumstellar material. Measuring the sizes of stars is difficult, primarily because of their vast distance and the complex structure of their outer layers. Such stars as WOH G64 are not only distant, but also shrouded in dense dust clouds, making direct size measurements difficult. The variability of these stars adds yet another layer of complexity, as their outer envelopes can expand and contract over time, changing their apparent size. In addition, the brightness and luminosity of these stars can lead to error in observations. The intense light can obscure the true edge of the star, making it difficult to determine where the star ends and the surrounding nebula begins. This ambiguity was a significant factor in the initial reassessment of the size of a large number of stars. The path to understanding these celestial giants also forces us to confront the stellar evolution limits in the Milky Way, often referred to as about 1,500 solar radii. This limit is related to theoretical limits on how large stars in our galaxy can become. The main factor determining a star's size and evolution is its mass. More massive stars have stronger gravitational forces that compress the core, resulting in higher temperatures and pressures. In the core, hydrogen atoms fuse to form helium, releasing energy in the process. This energy counteracts the gravitational force to collapse the star, keeping it stable. The limit of 1,500 solar radii is often associated with the Humphreys-Davidson limit, named after astronomers Roberta M. Humphreys and Chris Davidson. It denotes the region of the critical threshold on the diagram beyond which the luminosity of a star becomes so extreme that it can lead to its destabilization. In our case, it was an important milestone in the reassessment of the size of Stephenson 218. The initial classification of Stephenson 218 as one of the largest stars was called into question by its luminosity, which exceeded the Humphreys-Davidson limit. This paradox suggested that either our understanding of stellar physics needed refinement, or that the star's size was overestimated because of the difficulty of measuring such distant objects. It's also interesting that stars approaching or exceeding this limit experience significant mass loss due to a powerful stellar wind. The intense radiation pressure created by their extreme luminosity stimulates mass loss, forcing the star to shed its outer layers. Eventually, stars that have exceeded the limit of stellar evolution face an unsafe fate. When their core can no longer withstand the gravitational pressure, it rapidly collapses, leading to a cataclysmic supernova explosion. These explosions are some of the most energetic events in the universe. They scatter heavy elements into space, often leave behind compact remnants such as neutron stars or black holes. Exploring these limits highlights the delicate balance between mass, luminosity, and stability that allows these colossal stars to exist. It provides invaluable insight into the life cycles of the universe's most massive inhabitants. In the cosmic scene, size and mass often go hand in hand, but there are intriguing exceptions to this observation. It's natural to assume that the largest stars should also be the most massive, but the universe has a knack for refuting our expectations. This paradox is perfectly illustrated when we delve into the realm of colossal stars such as BAT 99-98. BAT 9998, a supergiant star, located in the large Magellanic Cloud constellation Doradus, boasts a colossal mass far beyond what we might expect based on its radius alone. With a mass of 226 solar masses, BAT 9998 is one of the most massive discovered to date, if not the most record-breaking. Despite the exceptional mass, the star is not remarkable for its large size. Its radius is 37.5 times that of the Sun, which corresponds to the size of a polar star, a white supergiant with a mass of 5.4 solar masses. However, as expected, both BAT 9998 and Polaris are not among the largest known stars. Residing in the Tarantula Nebula, a huge stellar nursery, it's among the most massive and brightest stars. BAT 9998 is rivaled by a close fellow Wolf-Rayet star, R136A1, located in the R136 cluster near the center of the Tarantula Nebula. As for the fate of such a star, BAT 9998, like many similar stars, is a candidate for supernova or hypernova. The exact outcome depends, of course, on the amount of mass lost. A supergiant may produce a gamma-ray burst and leave behind a neutron star or black hole, or it may not produce a visible supernova at all. In general, the life cycle of stars is quite intriguing. Stars begin their lives in the cold, dark corners of the universe in vast molecular clouds. These clouds, rich in gas and dust, serve as cosmic nurseries where gravity pulls the material together to form the heart of a new star. As the nascent star's core becomes denser and hotter, a dramatic transformation takes place. Nuclear fusion begins, turning hydrogen into helium and releasing a torrent of energy that lights up the cosmos. This fusion process is the star's powerhouse, the engine of its luminosity and heat. For stars like our Sun, this harmonious balance between gravitational forces and nuclear energy keeps them going for billions of years. However, this stage is only the beginning of their cosmic journey. As stars age, their fuel begins to run out. The Sun, for example, will undergo a dramatic transformation, becoming a red giant. This expansion is a paradox. Even as a star sheds its outer layers into space, it increases in size, becoming a huge, glowing ball of light that can engulf the inner planets of the solar system. But the life cycle of a star is not only a story of growth, it's also a story of loss. As the red giant phase fades, stars like our Sun shed those outer shells, forming ethereal structures known as planetary nebulae. The remaining core, stripped of its former glory, becomes a white dwarf, a dense, dim remnant of the star's heart. For more massive stars, the end is even more spectacular. Their demise comes in the form of a supernova, an explosion of unfathomable scale and beauty that eclipses entire galaxies for a brief moment. What remains may be a neutron star, or, if massive enough, a black hole. In this grand cosmic cycle, stars are not just points of light in the night sky. They are the forges of the universe, the creators of the elements that make up the world around us and within us. From their fiery birth to their spectacular death, stars are the architects of the cosmos, shaping the universe in their own image, one stellar life cycle at a time. Giant stars of enormous luminosity and size serve as cosmic beacons that illuminate the mysteries of the formation and evolution of the universe. By studying them, astronomers unravel the complex tangle of stellar life cycles, from the initial collapse of molecular clouds to the explosive finale of supernovae. The theoretical limits on the size of stars are still subjects of fierce debate among astrophysicists. However, in the realm of cosmic records, the title of largest star remains a dynamic prize. Discoveries and improved observational techniques are constantly revising the upper echelons of the stellar sizes. This fluid nature of space records once again emphasizes the vastness of the universe and the constant search for knowledge that drives our exploration of the cosmos. So, let's stay inquisitive as we eagerly await the discoveries that our universe holds. In the hidden corners of our universe lurks a silent force that sets everything around it in motion. Not light, not matter, but a mysterious entity that we have barely begun to unravel: dark energy. For many years, it has eluded the grasp of our best minds, gathering dust on the shelves of theoretical cosmology. Today, we stand on the threshold of revelation as new evidence suggests that we may have been mistaken about the very nature of this mysterious force. Could it be that what we thought was unchanging is actually changing before our eyes? Join us as we delve into the depths of space, guided by the latest data from the Dark Energy Spectroscopic Instrument, and embark on a journey that could redefine our understanding of the universe. To ensure we're all on the same page, let's first talk about baryonic acoustic oscillations, or BAO. These ripples, set in motion by intense pressure waves in the early universe, now serve as cosmic yardsticks, allowing astronomers to accurately measure vast cosmic distances. This complex cosmic interaction, a legacy from the birth of the universe after the Big Bang, provides us with a unique vantage point to scrutinize the fabric of the cosmos. In such a cosmic landscape, The Dark Energy Spectroscopic Instrument, also known as DESI, becomes a beacon of sorts. Armed with an array of 5,000 finely tuned fiber optic sensors, DESI is embarking on monumental tasks to meticulously map the three-dimensional positions of tens of millions of galaxies and quasars. This ambitious undertaking is designed not only to map the cosmic topography, but also to shed light on the shadowy force known as dark energy, which is believed to be the catalyst for the universe's accelerating expansion. Light is first reflected from the telescope's 15-ton primary mirror and then hits 6 large lenses that provide DESI with a wide, highly focused view of the sky, covering an area about 38 times the size of the full moon. These lenses are housed in a device that can be adjusted within millionths of a foot to keep the lenses aligned. After passing through the set of lenses, the light from the galaxy reaches the fiber optic cables at the DESI focal plane. At the very end of the telescope are 5,000 positioning robots, each carrying a single optical fiber, programmed to move to pre-selected sequences of galactic targets. This automated robot interaction allows DESI to target sequences of thousands of galaxies. Simultaneously, optical fibers that serve as DESI's eyes guide galaxy light down the length of the telescope to 10 spectrographs. These spectrographs are then used to obtain very accurate spectra of these objects and produce red colors for the various galaxies and quasars in the dataset. Each fiber optic sensor in the DESI array is a communication channel to the cosmos, guiding light from galaxies and quasars across billions of light years to the heart of the instrument. Robotic positioners ensure the jewel-like precision of each fiber's alignment to the celestial target. The fibers, each as thick as a human hair, are not just passive receivers. They are the endpoints of a complex optical path that begins in the depths of space and ends in the device's spectrograph. Here, the captured light is scattered into its constituent colors. When DESI scans the heavens, it picks up faint echoes of distant galaxies, each carrying a cosmic history recorded in BAO. These measurements, similar to the cosmic Morse code, are carefully decoded and analyzed to reconstruct the history of the expansion of the universe. Through this painstaking process, DESI provides a glimpse into the past epochs, tracing the evolution of the universe from its turbulent youth to its current, more measured expansion. The importance of BAO in this grand narrative cannot be overemphasized. Astronomers are using this instrument to map the expansion of the universe with unprecedented accuracy. This method, based on the fundamental physics of the early universe, offers a reliable basis for testing our understanding of cosmology by refining our models of the underlying structure and composition of the universe. Through the lens of DESI, BAO is transformed from a cosmic echo to a powerful discovery tool. So how will the mission help illuminate the darkest corners of space? So, let's elaborate on BAO. Imagine that the universe is a vast ocean in which sound waves once freely propagated through the hot, dense early cosmos. These were not sound waves as we know them, but rather pressure waves generated by the complex interaction between radiation and matter in the nascent universe. This interaction gave rise to what we now call baryonic acoustic oscillations, a relic pattern imprinted in the distribution of galaxies across the cosmos. These ripples in the fabric of the universe give us a standard ruler for measuring cosmic distances with extraordinary precision. In the early universe, there was a competition between gravity pulling matter together and radiation pressure pushing it apart, which created oscillations, akin to sound waves. When the universe cooled enough to form atoms and radiation separated from matter, these oscillations froze in place, leaving a noticeable pattern in the distribution of galaxies. The peak of these oscillations, at an interval of about 150 million light-years, serves as our cosmic ruler. This cosmic ruler allows astronomers to measure the expansion of the universe in a unique way. By examining the distance between galaxies and comparing it to the expected distance from the BAO, scientists can calculate how much the universe has expanded since light was emitted from these galaxies. This method also allows direct measurement of the rate of expansion of the universe at different epochs of time, which provides clues to the nature of dark energy and its impact on cosmic growth. In turn, the Dark Energy Spectroscopic Instrument can use BAO's measurements to produce an unprecedentedly detailed map of the expansion of the universe at different epochs. Located atop the 6,880-foot summit of Mount Kitt in Tucson, Arizona, which offers panoramic views of space, DESI uses a battalion of robotic fiber optic sensors in its quest to understand the accelerating expansion of the universe. Peering into the night sky, the instrument captures the light of millions of galaxies and quasars. By measuring the red shift of the light from these celestial objects, DESI can determine how fast the universe has expanded at different times. The instrument's precision allows it to detect subtle BAO imprints in the large-scale structure of the universe, turning these measurements into a detailed three-dimensional map of cosmic expansion. This map is not just a collection of data points. It is a timeline of the history of the universe from its early, denser state to its current accelerated expansion. By comparing the observed BAO scale at different distances, and therefore at different times in the history of the universe, with what we expect from our cosmological models, DESI tests our understanding of dark energy and the fundamental nature of the cosmos. The beauty of the DESI approach lies in its ability to explore different epochs, offering a window into the expansion of the universe over billions of years. This huge period allows researchers to trace whether dark energy remains constant over time or evolves. So, what was the purpose of this study after all? As we know, the accelerating expansion of the universe, a phenomenon at odds with the flowing forces of gravity, has revealed the existence of a mysterious component known as dark energy. This discovery, made in the late 1990s through observations of distant type Ia supernovae, revolutionized our understanding of the cosmos. Dark energy, which makes up about 68% of the total energy content of the universe, has a repulsive force that opposes the gravitational pull of matter and thus accelerates cosmic expansion. It was she who laid the foundation for the Lambda cold dark matter model, at a time when the disparate observed properties of the universe seemed mutually inconsistent and there was no consensus on the composition of the energy density of the universe. The model successfully announced a wide range of astronomical phenomena, from the large-scale structure of the cosmos to anisotropy in the cosmic microwave background. Despite the complexity of the universe, the Lambda cold dark matter model is relatively simple and characterized by a small set of parameters. These include the Hubble constant, the densities of dark matter and dark energy, and the initial conditions for the existence of the universe. The predictive power of the model allows astronomers to test its validity with observations such as the distribution of galaxies and the cosmic microwave background. The Dark Energy Spectroscopic Instrument has provided new insights into the mysterious nature of dark energy. By analyzing more than 6 million extragalactic objects at vast cosmic distances and different epochs, DESI provides reliable measurements of the expansion history of the universe with previously unattainable precision. This extensive data set, covering a redshift range from 0.1 to 4.2, allows us to reconstruct the expansion of the universe in detail and reveal the influence of dark energy throughout cosmic time. One of the most intriguing results from the first year of DESI observations is the indication that dark energy may not be a static force, but may evolve. This hypothesis stems from the subtle discrepancies observed between DESI measurements and the predictions of the Lambda cold dark matter model. In particular, the data collected in this study suggests that the parameter of the dark energy equation of state is close to being consistent with the cosmological constant. However, if we extend the lambda model and add a time-varying dark energy equation of state, the DESI data in combination with the cosmic microwave background or type Ia supernovae definitely indicate a departure from the model. This means that the influence of dark energy may not be constant, but may change with time. This preference persists in different combinations of data sets, indicating deviations from the lambda model. The data obtained in the survey, especially the discovery of dark energy, poses a serious challenge to the lambda model. Traditionally based on the representation of dark energy as a constant component, the detailed mapping of the cosmic expansion history with the instrument provides data that may require modifications to the standard cosmological scheme. In particular, the parameters present-day value and rate of change of the dark energy, indicating the variation of the dark energy influence with time, indicate a deviation from the lambda assumption of dark energy represented by the cosmological constant lambda, which requires a critical reassessment of the model's functions. The results of the paper have profound implications. If the dark energy equation of state does indeed change, this could lead to a major revision of our ideas about the expansion of the universe and its ultimate fate. Such a paradigm shift will not only refine our understanding of dark energy, but would also affect the broader cosmological models that describe the composition, structure, and evolution of the universe. To integrate these ideas, cosmologists may need to explore new theoretical frameworks or improve existing models to account for the time-varying dark energy component. This may require developing more sophisticated models that account for the dynamical behavior of dark energy or revising our understanding of the interactions between dark energy, dark matter, and other cosmological parameters. One intriguing alternative is quintessence, a dynamic form of dark energy with a changing equation of state. Unlike the cosmological constant lambda, which remains constant throughout cosmic time, quintessence is a field that evolves, potentially providing clues to the observed divergence. Could the changing nature of dark energy be a manifestation of quintessence? This model allows the effects of dark energy to vary, potentially consistent with the evolving equation of the state of dark energy hinted at by the study. The possibility that dark energy interacts with dark matter or other components of the universe also opens up an exciting paradigm. Such an interaction could lead to observable effects on cosmic scales, potentially explaining the changing equation of the state of dark energy. Another intriguing but radical proposal is the concept of early dark energy. This model suggests that dark energy played an important role not only in the late universe but also in its early stages, leaving imprints on the anisotropy of the cosmic microwave background and large-scale structures. This may offer a new lens through which to interpret the findings, especially if dark energy effects have been woven into the fabric of the cosmos since its dawn. The viability of each of these theories depends on consistency with observational data at various scales, from CNB anisotropies to galaxy clustering and supernova luminosity distances. The contribution of this project lays the foundation for future research in cosmology, as DESI continues to produce an unprecedentedly detailed map of the cosmic web during its 5-year mission. It's expected to inspire several future projects aimed at delving deeper into cosmological mysteries. These future projects will likely build on DESI's findings, utilizing advanced observational techniques and theoretical models to further explore dark energy and its impact on the cosmos. A discussion between study participants Sheshadri Nadatharand, and Adriu Font-Ribera emphasized the collaborative nature of this search, emphasizing the integration of DESI data with other observations to create a more complete picture of the evolution of the universe. Such a collaborative approach is essential to deepen our understanding of dark energy and its role in shaping the ultimate fate of the universe. Although the instrument's results challenge our current cosmological models, DESI's journey is far from over. It is merely a prologue to a much larger cosmological narrative, and standing at this threshold, we remind ourselves of how much we still have to learn about the structure of the universe. In a cosmos where distance is measured not in miles but in years of light travel, there's a star whose journey to us defies the usual cosmic scale. It is Arendelle, a luminary so distant that its light left it more than 12 billion years ago. By comparison, the light from this star began its journey to us when the universe was less than 1.4 billion years old. It crossed the vastness of space-time to reach us here on Earth. By comparison, the Sun is only 8 light minutes away. At the same time, the Arendelle light reaching us has been traveling through space since the earliest life forms formed on Earth. Discovered by the eye of the Hubble Space Telescope, Arendelle emerged from the darkness like a clue from the greatest detective story in history. It's not just a star, it's a record breaker, the most distant star we've ever seen. Arendelle's light has traveled more than 12 billion years to reach us, starting when the universe was barely 1.4 billion years old. So how did we manage to detect such a distant object, and what does this discovery tell us? In our desire to map the cosmos, astronomers have long sought to push the boundaries of observable universe. This domain is defined not only by the capabilities of our instruments, but also by the speed of light itself. On this cosmic horizon, every star and every galaxy is a potential beacon of the past, inviting us to uncover its history. Meet Arendelle, a star at the very edge of this observable frontier. Its light, which occurred more than 12 billion years ago, gives us a rare glimpse into the era of the universe's history that's virtually unexplored. Contrary to conventional standards, this celestial was given a proper name from the beginning, indicating its rarity and significance. The star was christened Arendelle, the name of an Anglo-Saxon origin meaning morning star. The name Arendelle is particularly appropriate because it symbolizes the star's role as the harbinger of the cosmic dawn. The cosmic dawn refers to the period in the history of the universe several hundred million years after the Big Bang, when the first stars and galaxies formed, ending the cosmic dark ages and filling the universe with light for the first time. The Hubble Space Telescope was the instrument that brought Arendelle into our field of view. Hubble's sharp vision peering across the vast reaches of intergalactic space captured an image of this distant star. The initial observation was no ordinary discovery. It required the alignment of cosmic forces, the deflection of light through gravitational lensing, and tireless data analysis by astronomers who decoded signals amidst the cosmic noise. Arendelle appeared before us not as a fiery disk, as stars are often depicted, but as a luminous point whose details are obscured by the mist of time and space. Nevertheless, even this faint image is a treasure trove of information, the starting point for a journey of discovery that goes back to the earliest chapters of the universe itself. In the history of astronomy, few instruments have revolutionized our view of the universe as profoundly as the Hubble Space Telescope. Arendelle's discovery was the triumph of this great observatory. Astronomers using Hubble's advanced optics explored the universe looking for faint glimpses of light from the oldest stars. It was like looking for a needle in a cosmic haystack. Wide Field Camera 3, the workhorse among Hubble's suite of instruments, played a key role. Its sensitivity to ultraviolet light, which is often blocked by Earth's atmosphere, allows it to capture the high-energy glow of distant stars. The task was enormous. Arendelle's light during its marathon journey through space had dimmed and shifted to the red side to a fraction of its original intensity. Its detection required not only the right instruments, but also a confluence of favorable conditions. Scientists have always sought to unlock the mysteries of the distant universe, to look deeper into the cosmic expanse. Arendelle's discovery represents a significant step in this direction, as the detection of distant galaxies has historically been a difficult task. Usually, when astronomers turn their gaze to these distant corners, they discern only the brightest beacons, quasars, and blazars. These objects serve as cosmic beacons, their light enduring a multi-billion-year journey to reach us, though it dims at great distances. Until now, only a few galaxies have been detected at such vast distances, their presence revealed by the scant light preserved by space travel. But the fortuitous positioning of a star that amplifies its light has opened the door for us to see it. So, meet gravitational lensing, nature's own magnifying glass. This phenomenon occurs when the gravity of a massive object, such as a cluster of galaxies, distorts the space around it, bending the path of light from objects behind it, much like magnifying glass bends light to a focal point. Arendelle's discovery is a textbook example of gravitational lensing in action. Located behind a cluster of galaxies known as WHL 0137-08, Arendelle's light has been bent and amplified, allowing it to reach us across the vast expanse of the universe. Without this natural magnifying glass, the star's faint glow might have remained hidden and its mysteries unsolved. The importance of gravitational lensing goes far beyond Arendelle's discovery. It's become an indispensable tool in the astronomer's kit, allowing us to study objects that would otherwise be inaccessible to our most powerful telescopes. With lensing, we can observe the detailed structure of distant galaxies, observe events such as supernovae in the early universe, and even search for dark matter by mapping the invisible mass responsible for the lensing effect. Gravitational lensing also allows us to test the limits of our understanding of physics. It provides a laboratory for studying the behavior of light and gravity, offering evidence to support the predictions of the general theory of relativity. The role of this phenomenon in the study of distant celestial objects is crucial. It not only magnifies the light but also stretches the images across the beam of view, providing multiple angles of observation. This can reveal details about the structure and motion within these distant objects, offering a more complete picture of their nature. Thus, the cosmic quirk, predicted by Einstein's general theory of relativity, opened a window into the distant universe and was the key to the discovery of this star. Delving deeper into Arendelle's personality, we uncover the story decoded by photons traveling through space. The Hubble data is the Rosetta Stone that turned these ancient signals into a story of the properties of stars and cosmic conditions. From the data collected by Hubble, scientists have concluded that Arendelle is not only old, but extremely bright, far surpassing the brightness of our own Sun. Its brightness suggests that it is a massive star that burns its nuclear fuel rapidly and lives a fast and furious life by cosmic standards. The Arendelle light spectrum bears the fingerprints of the elements in the star's atmosphere. These spectral lines are a clue to its composition, showing that the star probably formed from the primordial material of the early universe. not enriched with the heavy elements that characterize younger stars, such as our Sun. The significance of the Arendelle find cannot be overemphasized. As a star at the dawn of the universe, it provides a rare glimpse into the era known as the Cosmic Dawn, a time when the finest stars and galaxies formed, forever changing the dark, blank canvas of our early universe. During this formative period, the universe was a place of profound transformation. The first stars were the creators of the first heavy elements, the building blocks for everything from planets to life itself. The baton of cosmic discovery passed from the venerable Hubble to the James Webb Advanced Space Telescope, and that represents a huge step forward. It's given us a better look at Arendelle, the most distant star ever observed, and thus opened a window into early space. Originally discovered by the Hubble Space Telescope, the true nature of Arendelle remained an agonizing mystery. Was it a single star, a dense cluster, or something else entirely? JWST has now dispelled the ambiguity by confirming that Arendelle is a single celestial body, possibly a star system with a main bright star at its center. Through spectral analysis, JWST has painted the star in its true colors. It is a B-type blue giant, a stellar giant with a temperature of 13,000 to 16,000 Kelvin and a luminosity nearly 1,000,000 times that of our Sun. This colossal star, similar to Regulus and Algulus of the Milky Way, is a testament to the grandeur of stellar evolution. JWST's revelations go beyond Arendelle. It shed light on the galaxy in which the star is located, known as Doga Rising. This galaxy, named for its shape, is believed to be the most enlarged galaxy discovered during the dawn of the universe. Gravitational lensing, a phenomenon that turns massive galaxy clusters into cosmic magnifying glasses, amplified sunrise arc's light by 1,000 times. This effect allowed JWST to observe not only Arendelle, but also the surrounding bright star cradles, providing clues to the formation of early galactic structures. These observations have opened up a lively region of space with young star clusters less than 5 million years old, actively producing new stars. JWST's research on these clusters may one day solve the mystery of globular cluster formation, an enigma that has puzzled astronomers for decades. Arendelle, a star of immense brightness and age, is not an isolated wonder but a key to the broader cosmic landscape of its time. Together with neighboring objects, it forms a puzzle that, put together, can reveal the conditions of the early universe, a time when the cosmos was a frontier of formation and transformation. The area around Arendelle is a field rich in data. The light from these objects carries signatures of a young universe, encoded in wavelengths stretched by the expanding fabric of space. By analyzing this light, astronomers will be able to decipher the chemical composition of the early universe, understanding the prevalence of elements and the conditions that led to their formation. The vicinity of Arendelle is particularly intriguing because it represents the region where the first galaxies formed. Stars in these galaxies are candidates for what astronomers call population 3 stars, hypothetical first-generation stars born from the primordial gas that filled the universe after the Big Bang. The search for population 3 stars is one of the holy grails of modern astronomy. These stars, formed from the pure hydrogen and helium of the early universe, were massive, hot, and short-lived. Their existence is key to understanding not only stellar evolution, but also the epoch of re-ionization when the opaque universe became transparent to light. The discovery of a population 3 star would be akin to the discovery of a living fossil, an object that, against all odds, provided direct evidence of the first chapter of stellar evolutionary history. Such a discovery would confirm theories about the early universe and provide unprecedented insight into the birth of the first complex atoms. Arendelle, while not a population 3 star, is a beacon pointing us to this elusive population. Its existence in the galaxy since the origin of the universe suggests that we are looking in the right places, that remnants of these early stars may be hidden among the data that we're already collecting. In their quest to unlock the secrets of the early universe, Arendelle and his contemporaries are more than just points of light. They are breadcrumbs leading us back in time to the very threshold of the cosmic dawn, where the first stars ignited the darkness and lit the universe with light.